you need to clarify. Otherwise, I'm just going to kind of go from the beginning to the end and try to tell you the things that I think you need to make sure that you know. All right, so we begin with an apparatus. The apparatus has, come on, be nice. Two little masses on the end with a board in between, or a pole in between. And then it has a pipe. It comes down to a table. And then we have a string off the side with a pulley and a hanging mass. All right, so that's kind of where we begin. So the first thing I notice is that they use certain variables that I want to be very careful to use the same notation that they use. The first thing that they do is they say that this length right here is 2L. They also say that this mass right here is 4M in contrast to the M and the M that are on either side that are spinning. The next thing that they tell me is that they straight up give me the moment of the apparatus. And they tell me the moment of the apparatus is 2mL squared. And so that takes care of almost everything. The last thing that they tell me is this radius right here. And I'm just going to make a note that that's the radius, but that is the radius of the pipe. So it will be important to me when working on my torque. All right, so the first step in any of these problems is to simply do a free body diagram. So we mentioned this when talking about the lab, but the first thing I know is that there is a weight force or a gravitational force right here that actually causes the whole thing to spin. There is also a tension force that's pulling back on it from this rope right here. Now I am very specifically making my weight force bigger than my tension force because I know in order for this block to fall, it has to have a net force downward right here, which means this must be bigger than that. Not only is there a weight force and a tension force here, but there's also forces acting on the actual apparatus. Now because this is a massless and inertialess and frictionless pulley, this tension force right here off the side is going to be equal to that one right there. They're equal because that pulley is only bending the string. It's doing nothing else. And then if I was continuing my free body, I know that this would have a weight as well. We'll say the weight of the apparatus. And then this has a normal of the apparatus. And there's my free body. All right, so that's where I would begin. It's not just an extra fluffy thing to have a representation. It's actually useful because I may not realize this net force otherwise. Part A, if the downward acceleration of the large block is measured to be A, determine the tension, T, in the string in terms of the acceleration of the following block. Now as I'm doing this, I want to be really careful to only use the letters that they give me or the symbols that they give me. So for part A, I first look at my net force. And looking at this guy right here, the net force will be the big minus the little. So that's my weight force minus my tension force. And from there, I want to use their symbols, and I want to carefully start substituting in and get it into the format that they're looking for their tension force. All right, so first of all, I know my net force equals ma, Newton's second law. I know that my weight force equals mg. And I know that the tension force that they use is capital T. The next thing I know is that this mass right here is not just m, but it's 4m. So I want to carefully substitute that in at some point. So that is 4m times A and 4m times G. And now I'm almost there. It specifically wants to know the tension force, so I just need to wiggle this around and get it into a user-friendly format. So I'm going to move the T over here. I'm going to move the 4MA over there. So I get something like 4mg minus 4ma. And technically that's good enough. I would probably have multiplied that out a little bit and had something like 4m times g minus a. Either one of those is acceptable, either this or this. I'm going to put or right there to get your point. Now, not only did you have to have that answer, but you had to show some rationale with how you got there. So we would have needed a net force equation to start with, and that always comes from the free body diagram. So once we get through A, it asks us for B. Determine the torque exerted on the rotating pole by the string in terms of the mass of the blocks and the acceleration. So I'm looking for M's and A's in my answer, and now I'm looking for torque. So for B, I'm going to remember that torque is equal to force times the radius. The nice thing in this problem is that they actually define the radius right here as R, so that makes it nice and tidy. And then the force that's pulled right here is the tension force. So I'm going to plug in T as their force times the R. And then the last step is really just to take what I found in part A and plug all of that in whichever format I had left it is fine. So I'm going to use the last line. Again, you could have used the other, but I'm going to say 4M times G minus A times R, so that was just a substitution for T. And then I'm going to make it a little prettier by saying 4MR times G minus A. And again, the format could have been slightly different, but that is my second point. You'll notice it's in terms of M and A. R is a variable that they gave you, and G is always acceptable because it's a constant. The other thing you notice here is I did not plug in 9.8 or 10 because there were no real values that were ever given to me in this problem. So I want to keep G in there. All right, that takes us to C. When the large block has descended a distance d, how does the instantaneous rotational kinetic energy of the apparatus compare with the value 4 mgd? Check the appropriate space below and justify the answer. All right, so here we go. Let's see if we can fit it in over here. For part C, if I'm thinking about this block falling, I know that the potential gravitational energy at the top is equal to the kinetic energy as it falls to the bottom. So I'm going to go ahead and put top and bottom. If it's at the very top, then that's the way that works. Interestingly enough, as I look at the gravitational potential energy at the top, I'm thinking about mg delta y, which in this case, I'm going to make our substitutions. The mass of the block is 4m. G stays the same, and they specifically call delta y big D. And so I'm going to put all that together, and interestingly enough, that's the quantity they want me to compare to, 4mgd. When the large block has descended a distance d, that means the height that it's at right now is d, how does the rotational kinetic energy compare with the value here? So right here at the top, before I let go, there's 0 rotational kinetic energy because the apparatus is not spinning yet. Once I let go, not only is there translational kinetic energy, but the apparatus is spinning, so we got both of them going on. So we could simply say that that equals the rotational plus the kinetic energy, which would be my 1/2 mv squared. They're specifically asking how this Kr compares, so I'm just going to isolate it. So you can see now that the rotational kinetic energy has to be less than that quantity because it's that quantity minus the translational kinetic energy. And there truly is a value for the mass, and it truly is moving. So less than is where we're going with part C. So I'm going to scroll a little bit so we got some room here. So the first thing that I note is that I have less than checked, and it is validated right there. And that's that point. And then it asks me some more information. Compare with the value of that. Let's see how many points I've got on C. All right, so the last thing that I needed to do to get the third point, because it appears that there are 3 points on C. Let me make sure I'm telling you exactly right. 4 points on C. That's the wrong rotational sheet. Just a second. There it is. 3 points again on C. All right, so the first one is For less than with some rationale. The second one is to show the math. And then the third one has to be kind of to summarize it. You've got to put it into words. And so you should say something like, see, how did I do it? Part of the gravitational potential energy is used in the translational kinetic energy as the mass falls. That would be enough to get the third point. So just to recap, you have to have less than with a legit rationale to get the first point. You have to show me some sort of math here to get the second point, where you're actually using that 4 MGD and the idea of having two kinetic energies. And then the third one is kind of justifying what the math
If the
said.
following students are in the building, please come to the social studies pod, room 1.407. Elson Jang, Gianni Mingo, Sam Nassab, and Anna Ramsden.
All right, that takes us to D. I'm going to read D, and then I'm going to flip the screen, and we'll do D on the next screen. D, if the rotational inertia of the pulley were large enough to have an effect on the experiment, would you predict your answers to be different and explain your response? This one was tricky because the word answers had a lot packed inside of it. So first of all, you had to tell me if it was going to be different, and then you had to go back to letter A, B, and C and address each one of those individually. So that's where all the points came in, 4 total points on D. All right, so the first thing, okay, we're going to scroll down. The first thing on part D is that yes, they would be different. So I need to actually say yes, all would be different. I've answered the question and now I have to justify it. So now we're saying that there is inertia in this pulley. Suddenly the mass matters. Suddenly, instead of this string just changing directions, there is a resistance there that we didn't have before. Some of the energy now has to be used to rotate this pulley instead of just changing the direction around the pulley. And because of that, it does something a little weird to our free body diagram. So let's say I have a certain tension force here and here that were originally equal, and they're not equal anymore. So this tension pulling off the pole is actually not going to be equal to this tension right here, because there's something in between that is more sluggish now, that has more inertia. So the net torque on, or the net tension on the pulley, no, that's not a good time. Sorry. See how it was worded on the answer key, so I'll tell you exactly the way it was. The net tension on the pulley is not the same in both ends because the tension on the block is greater than the tension on the pulley. So now, in order to make this guy spin, there has to be an extra force here in this direction to actually make it, like, these two can't be equal or that won't turn. So now this one has to be bigger than that one, or the mass at the pulley itself won't rotate. That's a little weird point, so we're going to add it right here. So first, the tension force on the pulley is not the same on each side. All right, so I'm going to say the tension on the mass has to be greater than the tension on the, we'll say the pole, to make the pulley rotate. Now part A specifically asks you about the tension. So the reason I'm addressing the tension here is because I'm going from A to B to C and addressing one at a time. So here are our points. The first one is the different, and I'm justifying it. The second one is I've addressed part A. I'm going to put a little A here with the tension. So now I want to go to B. So I'm going to reread B. Part B, it asked me about the torque that was exerted on the rotating pole by the string in terms of the mass of the blocks and the acceleration. So now I need to know if the torque would change, and we said it would. And so now we want to talk about how the torque would change. So now we're going to say that the torque, well, that's not the way I started it. We're addressing torque. But the first thing I would say is that the mass and the gravity and the radius stay the same. But remember, your torque is your tension force times your radius. And so since the tension force changed, everything else would change. Let's see. All right, so all of those are the same. It tells me that the acceleration would be less. Which is what part A was talking about, the tension versus the acceleration. So the acceleration would be less, and therefore, because of the sluggishness of the pulley, it would be less because you can say the inertia of the pulley, the new mass of the pulley, the new energy used to rotate the pulley, however you want to say that, but it would slow down the system. So that is the next point relevant to part B. Part C had asked us, when the large block is descended this distance, how does the instantaneous rotational kinetic energy compare? So now we're looking at energy for part C. So for part C, so the potential gravitational energy of the beginning is the same, first of all. But there is less translational energy with less acceleration because it's moving slower. And so some of the energy, because some of the energy is used to rotate the pulley. That is relevant to C and the energy. And that takes care of the very bulky D. E is much more streamlined. E, how will the angular velocity of the apparatus, of the rotating apparatus, and the linear velocity of the falling mass compare now with the values that were calculated in parts A, B, and C? All right. So for E. So first of all, if I have less acceleration, the acceleration is less, then that means, and the distance stays the same, then your final velocity when the object hits the ground is less, because it didn't accelerate at as fast a rate, and so it just ends up slower. And they want you to make reference to how you know this. So when I'm thinking about this, I'm thinking about kinematics, and if the D is the same, how is the VF affected in the case of an acceleration? So it would be nice to make reference, and they expect you to a kinematic equation that is most relevant to this. So the only equation where I have a distance and a final velocity in the same equation is this guy, where we have VF squared equals V naught squared plus 2AD. Now you'll notice I used the big D there because that's what's relevant to this particular problem. So what that means is if this stays the same and this acceleration is less, then therefore this will be less because it starts at rest. And so I'm making reference to how I understand the kinematics. That's your first point. And then the second one part asks you about rotational velocity. How will the angular velocity also come into play? And most people got this part of it. I was pleased. So basically, it's just remembering that V equals omega R, or that omega equals V over R. So because the radius stays constant, as the velocity gets bigger, the angular velocity gets bigger as well. So to get the point, you needed to state the formula again, and then we're just going to make a statement. As the velocity increases or decreases, what do we do? We decrease, my apologies. Decreases, omega decreases. All right. And that takes us through the very ugly FrQ. I have seen a couple of different renditions where instead of talking specifically about energy, it has been said that there was work done here or work done there, and the work took the energy out of the system, and that's acceptable to talk about it that way. But this was probably the most straightforward. And if you addressed in D, if you specifically addressed the information A, B, and C, and then said they were all different, that's kind of what they were getting you to do. I do wish that where it said answers, that they had like bolded it or something. So you didn't lose the fact that you had to go back and talk about all of them instead of just like a blanket statement. Okay? All right, general questions before we end the video. Are we okay? That helps some. Yes? All right, thank you guys. Actually, you want to turn our video off?